Okay, so to find the velocity of the SUV before the collision, you needed to solve for momentum. So after solving for, and you have to solve for momentum by adding m1 and v1, m1 times v1 plus m2 times v2 after the collision, which got you 32,077 kilograms per meters per second. So um to find the velocity of the SUV before the collision, you know that the momentum has to be conserved since it's a collision. Therefore, um, the M1 times V1 plus M2 times V2 before the collision has to also equal 32,000 77 kilograms per meters per second. And since the velocity for the sedan before the collision is zero, the only one you have to worry about is the M1 times V1 for the SUV. So you would divide 32,000 um 77 by 3,200 kilograms, which is the mass for um um SUV before the collision to solve for velocity. So after you divide that, you get 10.02 meters per second, which is the velocity of the SUV before the collision. And like I said, for the velocity of the sedan before the collision, the sedan is at rest at the before the collision, which means it's not moving. So if it's not moving, that means the velocity is going to be 0 meters per second. To find the velocity of the SUV after the collision, you had to use kinematics because we were given the skid marks, which counts as the displacement, the braking rate, which serves as the acceleration, and the final velocity, which is zero, because at the end of the collision, it's going to come to a complete stop. So therefore, you need to use the kinematics equation: v squared equals v naught squared plus 2a times displacement to find the initial velocity, or in this case, the velocity of the SUV right after the collision. So when you use that equation and you plug in your values, you eventually get um 9 equals v naught squared, and then when you find the square root of that, you get 3. So therefore, the initial velocity, or the velocity of the SUV directly after the collision, is going to be 3 meters per second. So for the velocity of the sedan after the collision, it's the same process. You have to use the same kinematics equation because you were given the acceleration, the velocity, and the final velocity at the end of the collision, which is zero, and then the skid marks, which serves as displacement. And by the way, acceleration must be negative because it's the braking rate, which means that it's decelerating. So it has to be negative. Um, so you use the same equation: v squared equals v naught squared plus 2a times displacement. So when you plug in your values, you eventually get to 140 equals v naught squared. So when you find the square root of that, you get 11.83. So the velocity of the sedan right after the collision is going to be 11.83 meters per second. The type of collision is an inelastic collision because while momentum is conserved, kinetic energy is not conserved. So when solving for to prove that, you have to solve for kinetic energy, and you know that momentum is going to be conserved because it's a collision and momentum has to be conserved regardless of the type of collision. Momentum has to be conserved. The deciding factor of the type of collision, whether it's elastic, perfectly inelastic, or inelastic, is whether or not kinetic energy is conserved. So when you solve for kinetic energy, you have to use the equation 1/2 times mv squared, and you have to find the kinetic energy for each car before the collision and after the collision. Add it and add it. So when you find the kinetic energy for the SUV before the collision, you get 160,640.64 joules. So when you find the kinetic energy for the sedan before the collision, it's zero because the velocity is zero, and zero times anything is zero. So the total kinetic energy for the collision, for the system before the collision, it will be for the cars before the collision will be 160,640.64 joules. So then you do the same process to find the kinetic energy after the collision. So you have to use the equation 1/2 mv squared for the SUV after the collision and the sedan after the collision. So when you plug in your values for the equation for the SUV after the collision, you get 14,400 joules. And then when you plug in the values for the sedan after the collision, you get 132,951.46 joules. So when you add those together, your total kinetic energy for after the collision will be 147,351.46 joules. And for a collision to be elastic, kinetic energy must be conserved. If it's not conserved, it's inelastic. So since the kinetic energy before the collision is more than the kinetic energy after the collision, kinetic energy is not conserved, making the collision inelastic.